Okay, we're going to see if this series converges or diverges. And the first thing that we do is look at this and change it to a function of x. So that's really, really simple. You just replace the n with an x. So f of x, the function that we're going to be looking at, is going to be 1 over the square root of x minus 4. Now we have to verify those three conditions. The first condition was that this function is always positive for x greater than or equal to 1. In fact, here we don't even care about greater than or equal to 1. We care about greater than or equal to 5 because that's where our series is. So it's actually a little bit more general, or actually more specific, because we can't have like 1 in there, and then the function's not defined. So it's a good thing that we're going from 5 to infinity, otherwise it wouldn't make sense. And what do we have? We have, well, it's just by inspection. If I am plugging in things that are 5 and greater, then 5 minus 4 is 1, 6 minus 4 is 2. They're all going to be positive down there, so that's great. Also, I'm not plugging in 4, so it's also continuous. So we can say f of x is greater than 0, that means it's positive, for x greater than 5, greater than or equal to 5. So that takes care of the first condition. It's positive everywhere for the domain that we're concerned with. And then it's also continuous. F of x is continuous. This is just by looking at it. You don't really have to prove anything. So it's continuous for x greater than or equal to 5. So that takes care of that. Now the second part, or I mean the third part, verifying that we have a decreasing function. So how can we do that? Well, decreasing means that the slope of the function is negative. So if I take the derivative and it's negative for any value that's 5 or greater, then I have verified that third condition. So what I'm going to do next, I'll do it in blue, is I'll take the derivative of f of x. That's low d high minus high d low. The derivative of the bottom, that'd be using chain rule, but there's just a derivative of x is 1. So we have low d high minus high d low. That'd be 1 over 2 square root of x minus 4 times 1, all divided by the low squared, so that would just be x minus 4. And I'm going to check that real quick. Yeah, I think so. So I'm going to simplify this a little bit. F prime of x equals negative 1. That's actually important. Negative 1 over 2 times x minus 4, square root of x minus 4. Now you might be thinking, wait a minute, if I plug in some negative here, won't I get a negative divided by a negative? Actually, you get an imaginary number, but we're not concerned with the entire domain of this function. We're actually concerned with just x greater than or equal to 5, because that's what we're dealing with here. So if I plug in something that's greater than or equal to 5, I get a positive. Greater than or equal to 5, I get a positive. And then this is going to be a negative every single time, so it's a negative divided by a positive. We get negatives, so we can now say f prime of x is less than 0 for all x greater than or equal to 5, and that has verified our third condition, and we can use the integral test now. So what does the integral test say? It says if the integral from, it said 1 to infinity, but we're dealing with 5 here, so we're going to take the integral from 5 to infinity of f of x, which is just 1 over the square root of x minus 4. So that's what we're going to do, dx. So now we have to evaluate this. If this converges, so does the series. If this diverges, so does the series. And that's really all we're doing. So let's see if we can figure this out. I'm going to use u sub, u equals x minus 4 du equals dx. Great. And I will change this limit as b approaches infinity, and then the integral from 5 to b. Well, actually, I guess I'll be changing that, won't I? So I'm just going to circle this. I'll put it on later. I'm changing these, so I'm going to do an improper integral for the whole time, and then I'll switch it back. So this would be 1 over u to the 1/2 du, and then that's the same thing as u to the negative 1/2. I take the antiderivative, du. Take the antiderivative, that means I add 1. So adding 2 over 2 to that would give me positive 1/2. Multiply by 2. I'll take the derivative just to make sure. Bring the 1/2 down, that cancels. And then subtract 1, that's negative 1/2. Yes. Okay. And then normally it would be plus c. However, I want it to be not a indefinite integral. I want it to be a definite integral. So I'm going to put the x minus 4 back in. So I have 2 times x minus 4 raised to the 1/2. And now I'm going to put my limits of integration back, which were going to be 5 and infinity, but I'm going to change it to b and have the limit as b approaches infinity, because that's how I evaluate an improper integral. And then I'll substitute. So I'll put in 2 times the square root. I'm changing that to a square root. B minus 4 minus 2 times the square root of 5 minus 4. And I have the limit as b approaches infinity. So this part looks like goes to infinity. Infinity minus 2. Well, that looks divergent to me. So we would say that the series diverges because, well, the improper integral diverges. So we'd say the series from n equals 5 to infinity of 1 over n minus 4 underneath the radical diverges by integral test. And that's it. And then that's all we have to do. Remember, if the integral converges, then so does the series. If the integral diverges, so does the series. If the integral converges to, say, like a number like pi, it doesn't necessarily mean that the series converges to pi. In fact, we can't say that. We don't know. It's actually an upper bound to it. But that's it. That's all you have for the integral test. Goodbye.